The rigorous calculation for sizing relief valves for supercritical fluids was first published by Ryan Oiderkirk. In this paper, he addressed a methodology based on the heating added to the fluid, and with the properties of the fluid, it is possible to calculate the relief load, the heat flux, and based on that, do the calculations for the orifice. He has shown in his paper that the maximum orifice, or the orifice to be chosen, it's not necessarily when we have the maximum mass relief rate or the maximum volumetric relief rate. In his procedure, we need to do an iterative calculation to find the required area of the pressure relief device. So to do that, first we need to assemble relief case information. So we need to have the basis conditions for our evaluation. We need to select proper method and assembly data, and it is in this point that the calculations proposed by Ryan is very tough for us, because he uses equation of states and tables from handbooks to do the calculations of the fluid, and that for sure gets a lot of time. So based on that, some years later, another author suggested a similar procedure to perform the same calculations, and we will verify that also. But just to get at the original one, we need to do a number of iterations, considering first the calculation of the heat input, and at this point it will be very important the information of insulation. So as you have seen in the standard API 521 calculations, there is no considerations for the heat input. After that, based on the heat input and in the delta T added to your case, you will do the calculations related to some properties of the fluid, like the enthalpy, the liquid density, the entropy, and we will do the calculations of the differences between the current interaction and the previous interaction. With that, we will be able to calculate the volume flow of the fluid and also the mass flow of the fluid. And considering that in the relief conditions, we will have a shocked condition that leads to an isentropic release, we will be able to calculate the mass flux of the system based on isentropic conditions. And with the mass flux and the mass rate and also some other constant, we are able to do the calculation of the orifice, add that to a table, and return with the iteration until we get the maximum calculation of the orifice area. As I told you, these calculations can be tough because are based on the select proper methods. Some years later, from Ryan's work, Richard Duane proposed a rigorous methodology for doing calculations for the designing of pressure safety valves in supercritical servers. In summary, Richard uses as basis for his paper the work developed by Ryan. But he, instead of using the equation of states to define the properties of the fluid, Richard recommends the use of a process simulation software. Richard's chart is very similar to Ryan's chart, but what is interesting in Richard's paper is that he shows how to get the calculations, how to do the calculations based on the normal operating conditions of the fluid. In this case, he gets the same example, N-butane in a vessel, and he shows how to get the fluid as a liquid condition to the supercritical condition, as I have shown to you during this video. So to follow his procedure, we need to have information related to the vessel, for the system related to the back pressure of the system, and also the critical information or the critical properties of your fluids. In fact, you need to know the properties of your fluids. Based on that, you need to do the heat transfer calculation for the system, and it depends on if exists or not a firefight system available. And the first point of the iterations is the relieving pressure and the critical volume of your fluid. So based on that, record the enthalpy, the entropy, and the CP/CV, and increment the iterations by the addition of 10 Fahrenheit to each interaction. The pressure, release pressure will be constant, but the temperature will increase. So for each new temperature, you'll find information of the specific volume, enthalpy, entropy, and CP/CV. And he recommends at least 5 steps or 5 iterations. Once you fill your table with this information, it's time to perform the calculations. So the first thing is to verify if the condition of a release is choked or not choked. Most often, as the set point of the pressure relief device is very high, the conditions of a release will be choked. And that means that the flow through the orifice will be sonic. And consider that it will be sonic with a constant entropy and the pressure as the choked pressure, we need to find what is the choked temperature. And with the choked temperature, we'll do the recording of the specific volume and also the CP/CV. With that, we calculate the fluid velocity through the orifice as a sonic velocity based on this equation, and we calculate the mass flux through the orifice for the choked condition, and that is a very important point. Because here, the mass flux is limited by the choked condition. So that's why we need to use the properties of the fluid based on the choked condition and not in the release conditions. That's done based on the heat input and also the delta specific volume divided by the delta enthalpy. It's possible to calculate the fluid volumetric flow, and with the fluid volumetric flow and the specific volume of the fluid, it's possible to calculate the mass flow of the system. And with the mass flow of the system and with the mass flux and the others constant, using a conversion factor of 0.04 to convert feet square to inch square, it's possible to do the calculation of the orifice. Verify that this calculation here for the mass flow is not correct. You need to fix that, and we'll see in the spreadsheet. So with this, you will have a series of orifice calculations, and you need to verify what is the biggest one. Important to mention that the ICs on safety analysis perform the supercritical calculations based on Ryan's procedure. And the API 521 already recognizes this procedure as an alternative procedure that can be used to define the orifice and also the flow calculation. So you can use the standard API 521 calculation to define your pressure relief device, but you can also use this alternative method based on Ryan's procedure and upgraded by Richard.